Yeah, hello. I think I'm having problems connecting today, but it's fine now, right?
Yes, Doc.
Yeah, so let's wait for the others to join and then let's see what happens. Mm.
Okay, that's okay.
Mm. I don't know how is someone in touch with Shadrach? It's been a while we've seen him.
So, we didn't get you.
Shadrach, is someone anyone in touch with Shadrach?
I don't know. Let me see whether I can have it.
Yeah, it looks like it's been a while we've had him on. Mhm. 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 Mhm.
Doc, please, I've called, but the number is not going through.
Uh, Maybe let's see. After this, we'll try and reach out to our team and see.
Okay, Doc. Okay.
Okay, I think we can start now. Huh? No, but we are still just 2 or 3 hours. I typed in the WhatsApp that we should join again. I don't know if we are joining. Yeah, let's start. Let's start then. Let's start. Mm, it's almost 6 o'clock, so we can start. All right. So good evening. Today we'll start with the second part. So it's going to be more of practicing or examples of what we've been talking about previously. So here we'll not go too much into the equations, but I think based on what we've discussed previously, we can follow the equations clearly and then we understand how to write the modeling equation for different reactors. So in chapter 2, we are going to look at batch reactors. We're going to look at different types of batch reactors. So in this lecture, we are going to consider the a normal batch reactor. Then we'll also look at how to model a semi-batch reactor. After that, we'll look at how to model a batch distillation withholder. So these are the three reactors we're going to talk about today. So let's start with the batch reactor. So I expect that at the end of today's lecture, we should know how to write the continuity equation for a batch reactor, a semi-batch reactor, um, a batch distillation withholder. We should also know how to establish the individual or what we call the component mass balance and energy balance for a batch reactor, a semi-batch reactor, and then a batch distillation rate holder. So let's start with the batch reactor. Batch processes are quite interesting but very challenging in terms of modeling because of their dynamic nature. And usually we use them in very critical conditions where you are more particular about a specific type of product, which sometimes the product formation or the product kinetics are very slow. And so because of that, usually we use batch processes in some of these environments and in some of the circumstances. So you see a lot of batch in pharmaceuticals because there are some medicines that are very specific and very limited in number. So with such, you must use a batch process to produce the medicine, or else you might not even get people to buy. And two, also, it's going to be very expensive, become difficult to sell. So we use batch processes a lot in the pharmaceutical industry. But in the petrochemical industry, we also use batch, but we use it depending on our feedstock and then also some other economics that surrounds the product we're trying to produce. So let's consider the batch reactor. This reactor, this is a generalized batch reactor. So what's happening here in this reactor is that you realize that this is the reactor. What you have here is the main reactor. So this is the reactor. Now, inside this reactor, the reactor has its own temperature, its volume, then it has the species in it. So it depends on the reaction that is taking place in the reactor. But with this reactor we are considering, we are looking at a reactor that has two different species that will be one will be depleting and one will be forming inside the reactor. Okay. And so you can see a temperature sensor here. This is usually used to measure the reactor temperature. And that's why if you realize from all the equations we've developed, I was telling you that there are some parameters we will always know. So if you know them, after you have written the equation, and you have those parameters, you can input them into the equation. Then it now allows you to simulate or to solve the equation and then understand your equipment very well. So with this batch reactor, what's happening is that we normally have products coming in here. So this is where the reactants, no, not the product, reactants will come here into the reactor. Then they will attain a certain level like this. Now, when it attains a level like this, or what we call the desired level, you close this valve. So this valve here is closed. Once this valve is closed, you now set the reactor to its required temperature. So this temperature controller here is what will help you to know if you have gotten the temperature you need the reaction to occur or not. So if this one gives you the go ahead, then what you do is you allow the reaction to take place. When the reaction is done, then you open the reactor here, and then you take out your feed, your product. You see, so that's how a batch reactor operates. But now, with this batch reactor, it has two things. It has a temperature that heats the reactor. So you can see that we have VJ here, this part. This is where this is where the heating of the temperature goes on. Then we also have what we call a cooling fluid here. This one, this part. This cooling water is used to balance the temperature in case there's increase in temperature due to the reaction. This one here is used to reduce the temperature. But this part here is used to um, heat the reactor. So the feed, the steam, we use the steam. You see the steam. So the steam comes here, then it comes out here. Then the cold water also passes through here. Then you put the cold water here rather. Then it exits here. So this is the exit of the cold water. All right. So having said this, we are going to now write what we call the mass balance equation for this. And then you are going to also write the energy balance for this. So we'll start with the mass balance. Then after that, we'll go to the energy balance. The first mass balance we'll write is the total continuity equation. And the total continuity equation has to do with what? Mass accumulated inside here. So the mass accumulated inside here should be equal to what? The mass input minus the mass output. But we know that whatever we put in here, we don't remove it in a batch process. We leave it there. When it's done, we take it out. So whatever we kept in is the same thing we are taking out. So therefore, the input will be equal to output. So you have a zero term for this. So you realize that the changes in mass with time in this is going to be what? 0 minus 0 because the input minus output. So this is 0. So it means that for a batch reactor, the total continuity of the total mass balance is always equal to 0, which means that the input is always equal to the output. Yeah. Let me go to the next slide, then we'll check what we have. Okay, let's clear all this. How do you clear? Yes. All right, so let's continue. So after, I think now we understand the whole process here, what this equipment is trying to do. Now, like yesterday, we were talking about a batch reactor can be anything. You can have a simple batch in your house. You can have simple batch in the office or anywhere. It's not really every time that you have a batch reactor in a plant or something, but you can have it in anywhere. This could just be a simple cooking pot or a rice cooker. A rice cooker is a typical example of a batch system. Because if you see what happens in a rice cooker, you open it, you open the rice cooker, put in your water and then rice and salt, then you close it. After that, you allow it to heat, right? When it heats to some point, then you open your rice is done, then you take out the rice. So you see that whatever rice you kept in and water and then the salt is the same thing you are going to take out. So it gives you the same equation. So let's look at the um, assumptions and maybe just talk about the description a little bit before we go to the equations. So we believe that we are saying that the reactant is charged into the vessel, which I've just said. And then we use steam, what, to heat the system through the jacket, or what we call the heating jacket. So this heating jacket uses steam to raise up the temperature of the system to the desired temperature. Then we have cooling water that is added to the jacket to remove the additional heat that is caused by the reaction. And they are also saying that the reaction follows a first order reaction for both the first and then the second. The reason why we haven't C here is because you are forming, the goal is to form this and this. Let me take the rice cooker, for example. If you are cooking rice, the goal is to get a cooked rice, which is B. So you put raw rice, let's say A, and you want to get a cooked rice, which is B. If you don't come early and check your rice and stop it or start eating at the right time it's cooked and you leave it for long, that cooked rice will start turning into a burnt rice. That is C. So we don't also want to waste too much time that B will start changing into C. So usually in a bad reactor, we always want to identify the right time at which we can get the maximum of this. Also, just similar to the rice cooker example, if you don't come at the right time to check your rice, you might come early and the rice will be uncooked. So you have a lot of uncooked rice in your rice, though some will be boiled, but some will not be what cooked. Especially those of us who like to do jollof rice. If you don't do it well, you see that sometimes some of the rice will not be cooked and some will also be cooked. It's because of batch temperature and timing. Yeah. So they are saying that the reaction here is a first order reaction. And the desired product is B, but if takes too long, it might turn into an undesired product, which is C. So we must make sure that we stop this very early. And that is what we call the optimum batch time. In some equipment, you might call it the retention time, but this one, we call it the optimum batch time. So let's look at the equation now. Now, for the batch reactor, the total continuity equation, as we said, is equal to 0 because input is equal to output. So it's going to be equal to, so the changes of mass, there's no accumulation in the system. The change in mass in the system is always equal to 0. Now, let's look at the individual component analysis because we had A coming in and it's turning to B. And if time not taken, it might go to C. So for the first one, we have A here. So what we'll do is we have to write what? Accumulation term. Then also we write the input and then the output. I think you remember that, right? So if this is our reactor here, we must know A, the input of A, and then the output of A. If you remember, A is what we kept into the system. So at this place, we'll know the concentration of A. So A will come at a certain concentration. There is it. And then it will fill this thing at a certain mass. Then here, A is 0. There is no A coming out. The output is either B or C. You get it? So the accumulation of A inside this reactor here, which will be the concentration of A. This is AO. That's initial A. And then here is the accumulation of A. is going to be the mole concentration. So from our previous equation, we're going to have this delta T, right? Should be equal to the formation, the depletion of A, which you remember is negative this V. I think we still remember this equation, right? So if we are using this, we know that amount is equal to what? Volume times concentration. So therefore, this here can now become what? CAV dt. Then this one, R is equal to KCA. If the reaction, if the order was squared, then we would have squared it. But it's first order reaction. So this is one. You get it? So that's why you have this here. So when you replace this, you know that this is what N. So it's going to be VC, right? So you have going to have the volume here. Then you have the concentration term. And then this becomes the continuity mass balance equation for A in the system. We can write the same thing for B. So for B, it will now take the same way. It's going to be the amount of B's. This shall be it. So it's going to be the amount of B, which is this, the T should be equal to what? Input of B, right? The mass input of B. But we know that at this part, initially, there's no B. B is equal to 0 here. So the input of B will be 0 minus the formation of B. That is this term here. This is the formation of B. No, sorry, this is the depletion. So this is the formation of B. So the formation of B is the opposite of the depletion of A. So formation of B will now be equal to uh, the volume. It's going to be positive. The volume of K1CA. Then the formation, the depletion of B, if B is not taken at the right time, B will also result what? To form C. So that's the depletion of B. Now it's because B will be depleting, it's going to be negative. So it's going to be depletion of B, which is V K CB. So this becomes the equation for B. Then we know that you can, from Arrhenius equation, you can use these terms here to represent the K. So you can rewrite this. So you can rewrite all of this by changing it with by substituting in the Arrhenius equation to have the complete continuity equation for the system. But we know that this Arrhenius equation comes in as what we call the constitutive equation, as we establish in, I think some previous days. Right. So that is for the continuity equation. When you are done, we have the total balance, we have the component balance. Then the next thing is to write the equation for the energy terms. So we now have to write the energy balance for this. So let's look at the energy balance. For energy balance, we assume what? A Lamb model. So you see that we are trying to assume that the temperature of the reactor is all lumped together with time. The temperature of the reactor changes with time. So we will not have Taylor series in our model to check temperature with respect to distance. We only check the effect of temperature with respect to time. So in the same way, that's what we do. We have this here. We have an output. We have an input, right? Then you have cool. This is the cool water, cool water out. And then you have steam, then steam out. And then you have the temperature in the reactor. Do you get the thing? And then you have reactions in the reactor also. So we now have to account for all the energy terms The first energy term, because it's a batch reactor, we are not flowing the reactants in, so we can't talk about that one. There's the inlet is not the reactor is not flowing in at a certain temperature, so that one does not really have a problem. So the accumulation of um energy or temperature in this will be what? Delta MH, you remember dt, where this is enthalpy, right? Is equal to mass H in minus mass H out, if you remember, plus or minus the heat generation term from the reaction. So we had what we call delta H I, if you remember, KCI, that's the concentration, right? Then we had plus Q. Okay, so this is the total mass we established the last from our previous lecture. So we're going to write this for each of them. So we know that this is what? This is H here is equal to Cp dt. Do you get it? H here is equal to Cp dt. And mass here is equal to what? Rho times volume. So when you substitute rho volume and then H dt, you have this here. So you now see that the accumulation term is equal to what? Rho v Cp dt on dt. Then the next one, we said that it's a batch reactor. There's no input, so this is zero. This is zero, so that one will not account. Then the next thing will now be the heat of reaction. So we account for the two reactions that are taking place. So for the first reaction, we're going to have this lambda here is the same as delta H. Okay, that's the exothermic heat of reaction for the first reaction. So this could have been 1 here. Then we have VK1Ca. You remember it is what? First order reaction. So it's going to be raised to the power 1 here. Then minus the second reaction, H2VKCb. Minus this one is this Q is the same as Newton law of heat transfer. So this is HIA T minus Tm. So it depends if it is from the cooling to the reaction or from the steam to the metal. That's how we assign this one. So this becomes the generalized energy balance for the process. After we do this, we'll now come and write the energy balance for the metal. The metal between the steam and then the reaction, there's a metal. We'll write the energy balance for that. And then we'll also write the energy balance for the fluid that is passing through the steam. So let's look at the energy balance for the metal. Energy balance for the metal will be equal to what? The temperature on the metal. So it's the same way. So you're going to just have delta MH of the metal over dt, right? And for the metal, what's happening? You are only having heat. You have, I think, cold and then hot, right? That's what is moving through it. So you're having a movement between the jacket and then the metal, and then also between the metal and then the reactor. That's this T. So it's going to be equal to Q as a result of the jacket minus Q from the reactor or the reaction. And this one here, the first one is this term. So it's going to be equal to what? The heat coefficient times the area into bracket temperature of the jacket, the steam, minus the temperature of the metal, minus the heat of the reaction, the reactor, times the area, times the temperature of the metal minus the temperature inside the reactor. So with this one, you can predict the temperature of the metal. So you can just divide through by this, and it will be well simplified. All right. So that is it for a barge reactor. That is it for barge. That's why I've written here that in elsewhere in this same handout, we use delta H as the isothermic heat of reaction. So just take note of that. All right. So that's how we model a batch reactor. The next reactor we're going to look at is a semi-batch reactor. Now, a semi-batch reactor is similar to the normal batch reactor, but the difference in semi-batch reactor is that there are two things. It's either the input is continuous or the output is continuous. So for this case, we have a reactor like this, and then you are trying to run this reaction in the reactor to form these products. Okay. Now, what's happening is that they have B, reactant B, and then reactant A. In this system, you will first put B in the system, then you flow A. A will flow continuously being added to B whilst B is consumed to form the products until the reactor reaches its required um, level. Then you stop flowing this. Then you take out the product. So you see that with this one, B is being flown in. So sorry, A keeps coming in at a certain flow rate. It could be very slow, it could be very high, depending on how the reaction looks like or the reaction behavior. That's what you use to define the flow rate of um, the reactor. So let's look at how to model this. Now, this also has a cooling water in here and cooling water out, just to control the temperature in the reactor. And it also has a heating system. It could be a heating coil, or it could be a steam manipulated jacket to maintain the temperature in the reactor. We could have either of them. That's fine. So let's look at how to write this one. But before we go there, we'll look at the general description, then we'll just write it. So it has similar assumptions to the general what's the name? The general batch reactor. However, the difference is just the flow term that is at the beginning here. The flow term here is just the difference. That's what makes it different from the other one. So let's look at how to model this one. Now, with this also, we're going to have the mass and then the energy balance. So let's look at the mass balance first. The first one we write is the total mass balance. So we come here. Total mass balance is what? Input should be equal to what? Output. In this reactor, we have input, but we don't have output. So output is what? Zero. But we have an input of this coming at a certain flow rate. And then at a certain density. That's A. So if you want to check this one, the total mass balance, which is going to be uh, this delta MDT will be equal to what? The flow rate of A times the density of A. Now, if the densities are the same, it means that we know that M is equal to density times volume, dt, right? It's equal to flow density. So density will cancel density out. So we now have the V dt is equal to the flow in. So therefore, the total mass balance for this system is what? The volume in the system is controlled by the flow of A. That is what it means. So this one here tells you that the volume in our system here, the volume here, this level here is controlled by how much of this will flow here. So if B was just here, the remaining volume will be controlled by this as the total mass balance. So that is what it means. But aside this, we'll now go and then do the individual component balance. All right. So let's try and then establish the individual component balance. So for the first one, which is A, so the component balance of A is going to be what? So you have N A dt should be equal to what? Input minus output plus or minus generation, right? If you remember. So we'll take the first one, A. If we take the reactor, let's look at our reactor here. You see the reactor? With this reactor, we had A. It was A that was coming in here. So A here has a density. It's coming in with a certain flow rate. So we can come here and establish that A, in terms of this concentration. So we can now say, you know that Na here is equal to V times Ca, right? So we can now come and write this as what? The differential of what? VCA over the P. So the T. So we can find the formation of A with respect to time here. And that should be equal to the flow rate times the concentration. Because we know that this mole here is the same as what? Mole is equal to uh, concentration times volume. And this is the volumetric flow rate. So this is volumetric flow rate, and this is concentration. So this will give you moles per time. You get it? So we can have that also in that system. So this one defines the input term. Then the generation, because there's no output of A. If you look at the reactor here, there is no output of A. So the generation term now follows what? The depletion of A. So it's going to be minus. So it's going to be minus, if you recall, the generation term usually is plus or minus RV. Do you get it? And we said R is equal to all right, maybe come back. Depletion term here plus or minus RV, right? And we said this one, the R is equal to K I to the power N, which is the order. And then there's a constant here for the equation. So if you see this equation here, this one is the V here. This one here is the reaction constant here. The coefficient, the reaction coefficient here for A is 2, right? So A is equal to 2. You can see it here. A is equal to 2. So that one has to appear in the rate of the reaction. That's why we have A here. This A is equal to 2. Then we have the K, and then we will have concentration of A and then TB, because these are the reactants and they are depleting, so it's supposed to be minus. So this will now give you the generation of the depletion of A, or with this equation, we can monitor the amount of A in the reaction. Now, there's something to note here. Let's look at this term here, dVCA dt. If the volume of the reactor is also varying, it means that we have to apply the chain rule. Like yesterday, we have to apply chain rule to separate this. So we have to differentiate each of them differently because they are all variables that are varying. But if volume does not affect this, it becomes a constant, then volume can come out, and then you have CA. Then you make CA dt the subject, then this can also hold. Okay. All right. Let's proceed to the second one. The second one is the formation of B. Let's go to the formation of B. Can you all hear, or is just Cornelius who has a network problem?
Oh, we can hear. I think it's going on.
So it's just from his own end, right? Okay.
Yeah, dog, you can hear, but sometimes it breaks.
Okay. Now Shadrach is
Yeah,
in.
it can help.
Yes, yes.
Yes, the luck is on.
Okay.
So it's going to your recording. Even some of us still follow after the whole thing. Thank
Yeah.
you.
So when we finish, I will upload the video in the Dropbox so you can still view it. Yes. Okay. So let's continue. So for B in the reactor, the same way we are still following this reactor, this one. So for B, initially we don't have B here. We had B. B was in the reactor here before we added the A to form the reaction. So B will not have an initial term. It wouldn't also have an output term because B is not coming out. When we finish, we are taking the product out. So the input and the output term for B. So if we write the continuity equation of mole for B, the T, which is supposed to be input, right? The mole input of B minus uh, mole output of B plus or minus the generation of B or the formation. B is also actually a reactant, so it will also deplete. So for this, you're going to have this one will go off, this one will go off, leaving only this. So it's left with one term. And so that is why you see that we only have one term for the generation of B here. And the same way, it's negative because B is being depleted. This is the volume, the reactor. This is the reaction coefficient of B in the reaction. Then it is 1, right? In the reaction, B is 1. Let's see. You can see that B is 1 here. The coefficient here is 1. So it's fine. Then we have the K, then we have CA based on the order. Now, if we have the K, we can change this to the Arrhenius equation, right? You can write this in terms of Arrhenius equation. Substitute it inside the equation. When you do that, it means you are trying to include the effect of the, what we call the constitutive equation, which is good and nicer. All right, so let's proceed. To the energy balance. Let's go to the energy balance for a semi-batch reactor. For the energy balance of a semi-batch reactor, just like the other one, you see, we have 3 terms here. So let me just make it 4. Let's say it's 4. Why are we having 4 terms here? We'll take each term one after the other and explain them. The first term here is the accumulation of energy. This term here is the energy due to due to the input feed. That's A, because A will be, we keep adding A at a certain temperature. So it will have an energy term. And then this one you see here is the energy due to what? The heat of the reaction. So this is the heat of the reaction. Then this one here is due to the Q. That's the energy term that is being added or removed. That is from the heating and then the cooling system. Okay. And so you see that QM here is equal to HIAI on this, where this one here could be what? From the heating jacket or the cooling jacket. This term, sir. Okay. All right. So with this, we can expand it this way. Originally, this equation was supposed to be like this. If we want to follow from what we've been writing previously, we're going to have um, delta mh dt equals to mh input minus mh output plus or minus what? Delta hi um you can do it this way. Okay. Then plus or minus the Q term, QI. So Q can be heat, steam added, or it could be the cooling. Okay, so in our case, they are using QN. Now, when you have this, you can break this down, right? Because we know that from here, the H is equal to Cp dt. Remember, then M is equal to what? Rho V. So therefore, the first term here is supposed to be rho V Cp dt. Let me use the capital temperature dt. Okay. Then the input term, which was this one, it's in terms of flow, right? So this one here will also give us what we call rho Cp Fo delta T, which is going to be the T that is being added, the temperature added minus the temperature in the system. Okay, because this product A is coming in with a certain temperature. So that temperature minus the temperature in the system. Then plus the temperature due to the reaction. So we know our delta H, we know our K. The reaction is A and CB. You get it? Times V. This is how it's supposed to be like. Supposed to be times V because there's V here. Okay, then you have plus QM. Now, when you have this, to simplify it to this, what you do is that you divide through by this side. You divide through by rho VCP. Divide through by this. So this will go off. So the first term becomes this, right? The second term, which is this, if you divide it by rho CP, the CP will go, this one will go, it will have it B. So that's why you have this term. And the next term is this one, it has V. So if you divide it by rho VCP, this V will go. So to be over CP. That's why you have this. Then the Q is alone. So if you divide it, you're going to have QM over V rho CP. And you have this term. So it's just a simplification of all the equations we've been writing. All right. Any question? All right. So let's go on until we finish. So after this, the next thing is to define the QM, which we say it is the heat that is controlled by that is being added or applied to cool down the temperature of the reactor. So that H here is also expressed as H times the area at which that heat is being added or moved, minus the temperature in the system and the temperature of the metal. Then you have that also. So when you do that, you're now left with two things. We have to also try to predict the temperature profile of the fluid in the jacket, that's the steam. So if you want to do that, then you have to write equation for the jacket, because see, here, if you consider this diagram here, you see that it's like this. So the heat is coming in, so it's also flowing. So there's an input heat, and then there's a heat applied. So if you want to write for that, you need to consider, where is it here? This is the wall. This is where you were. So this one here will give you the heat in the jacket here. Just like the previous one we did. There are two, right? So the jacket is like this. Let me explain it. You have the reactor this way. This is the jacket. This is the heating jacket. And then it has steam coming in here. The steam is coming in, and the steam is coming out here. So because it's coming in at a certain temperature. That's this one. And then there's heat that is being added. That is this KOJ from the jacket. So that heat that is being added to this steam here is what is causing this. But because when it comes here, it changes. So the heat that is added is this KO that you see here. So in the same way, you're going to have heat inside here, energy term inside here. That's the accumulation of energy. So the same way, the accumulation of energy here will be what? The volume of the jacket, density of the fluid in the jacket, CP in the jacket, times difference in temperature of the jacket, the T. This will be equal to the flow in. So it's going to be what? Rho CP flow times the changes in temperature between what? The heat that is coming in, that is this. The JO is the heat inside the jacket, right? And then the TJ is what? TJ is the heat of the jacket. So you subtract that one, the initial heat in the jacket here minus the temperature in the jacket plus the Q. So the same way when you divide through by VJ, rho J, CPJ, this will go. Then you have this term. Then this will divide by this, giving you this term. So this is the equation you can also use to control the temperature of the steam. So these equations are used in the control process. So if I want to adjust the temperature, I can use these parameters here to adjust the temperature of the system. So we use these equations mostly in control. So in the same way, you can calculate the temperature, the energy balance on the jacket wall. And that is given to you by this equation that we have here. That's the temperature by the wall jackets. All right. So any question on barge reactors also? There are no questions. We'll go to the last barge system I want us to talk about. Then our next lecture, we'll go to continuous processes. Then we'll look at processes that involve mass transfer also. So the last one we'll look at today is what we call the batch distillation with holdout. Now, batch distillation is mostly used to distill small products. And just like the multi-component distillation. You can use a batch distillation to distill several compound, but usually it's best if the components have a very good temperature gradient that can allow effective separation. So the energy consumption in a batch is usually very high, but when you use it economically, it's feasible. So it works. So people are able to use it sometimes. So sometimes, usually, they look at cost. If you can't spend money to buy an expensive distillation column, then you go in for a simple batch reactor that will help you. So this is how a batch distillation column looks like. Now, this is what happens. You have this one here, which sometimes we call it a reboiler. Some also say it's a steel pot, or it's just a pot that you boil in the thing. So the boiler has a heating source here. You see this queue here? That's the heating source, like a coil. So this boils the feed. So you put in the feed here, and the feed is here represented as MB. And that feed has different components in it, which is XBJ. So we can have XBJ1. So we can have XB1, XB2, XB3. It means that you have different what components in the reboiler. Okay. Then what happens is that they also have a tray here. They have 1 and 2 trays. They have 2 trays in their distillation column. So what's happening is you boil this one. You boil it through this. When you boil it, the component will start vaporizing. The vapor phase will start vaporizing. When it comes here, then it condenses here. This is a condenser. Condenses into liquid here. Now, in a batch distillation, we don't just take the product out. What we do is that we do what we call reflux. Because for the first round, if this one condenses here, you will not have a pure product. So what we do is we'll pump this, use this pump here, pump it back here, which we call the reflux. You see the R is there. So this is the reflux. We'll pump it in for several times. And when you keep doing that, it keeps giving you a better pure product. So when this becomes pure enough, then we want to withdraw it here as what we call the distillate, which is D. So the fluid that comes here is what we call the vapor. So you will see that the reflux will be equal to what? The distillate, the reflux here, what is coming in here, should be equal to, or rather, it should be equal to V minus D, right? So the vapor that is condensed here minus what you have removed is what gives you the reflux, the amount you are putting back to ensure that you have a pure product. So with this, we are supposed to write the mass balance for this process. We write the mass balance inside the reboiler, mass balance on the tray, and then the mass balance in the reflux area. That's what we do. So let's take a look at the general description. Then after that, we'll establish the mass balance equation. There we go. So a typical batch column or batch distillation column is normally designed such that there is a fresh feed which is charged into the spot, which you call it could be a reboiler, as I said. Then it will be heated until the material here or the substance here begins to boil. When it boils, the vapor will travel along this line. So you only have vapor here. And then the reflux liquid that keeps coming in. So what we have here is what we call the top tray. You see the NT. So it depends on the number of trays you have. So it keeps boiling. When it boils and then gets here, then it will hit down, comes back. Right? Then when it comes here, it now condenses into liquid. Then we allow a long period of reflux. When the purity is good, then we allow for the distillation. Sorry, we allow the distillate to come out. So in this system, we are going to say that the total column is run on what we call a total reflux. That's what I was saying. Complete reflux means that you don't just start withdrawing, you keep running the reflux because it's batch until you get a pure this and then you stop. Then you now withdraw your product. So until overhead distillate composition is the lightest component we need, which in this we are trying to say is the component one. So when this component one, which you call XD1, means that the component one in the distillate, it will reach the desired specification we need. Then we now stop the process. Okay. When we stop it, we now withdraw the product at a certain rate. Then we withdraw it and then we use it for what we want to use. So when you keep doing that, eventually what happens is that the amount of light components, which is a component one in the pot, will reduce because majority of it has been vaporized and withdrawn. So definitely, if you allow a good reflux, the amount of light component in the pot will reduce drastically. And this is due to what the increase in the purity of the light components in the distillate. And there will also be a period when the distillate contain too little of the component that is in the pot, right? And when this happens, you have a little bit of the second component also, at least inside your reflux more. You have a little bit of it. You will not have 100% of the first product. So you have a little bit, which you call the build-up. So if you are getting more of the heavy component in your system, means the build-up is more and your reflux is very bad. So you might not get a very good yield of your product. All right, so let's look at some few assumptions that we use in a batch distillation system. Theoretical trace. We use theoretical trace. We assume that the trace are theoretically working perfectly. And they are all under what? Molar equilibrium overflows. Means that there's no excess, there's no whipping and damping occurring in your system. And it is at a constant relative volatility. That's the assumptions we have. Then we also want to say that the total amount of material or product that we charge in the column is what we call MBO. That means that's the initial amount of product we have in the system. MBO. Then this material we call MBO here. MBO here has several components or compositioning. So it can have 1, 2, 3, 4, 5 components in it. And so all of this will be in the reboiler at the beginning. So the mole fraction of each, so let's say if it's component one, the mole fraction of component one in the reboiler will be what? XBO1. The next one will be XBO2. Next one will be XBO3. And when we add all this, we get 1, which is the same as the main MBO in our system. All right. The next thing is that the composition in the still pot at any time is, as I've said, XBJ. That is inside the still pot now, because when we start distilling, some parts will start leaving, right? So it's not all that will leave. So the initial is XBO, but at any point in time during the process, it becomes XB. So we also have what we call XB1. XB1 is not the same as XBO1. XBO1 is the initial of this, but at a certain point in time, this value will start reducing. This value here, initially, this is the same as this, but with time, this value will start what? Reducing inside the pot. So the reduction of this is what we call the XB. It's like what is remaining in the pot. If we take away, so at this part, the first component is 100%. So at time, maybe at 10 minutes, after 10 minutes, if we have 20% of this going into the vapor phase, it means that the XB1 in the pot now is now 80% of the initial. So XB1 is not the same as SBO1. And the same thing is that because we start losing some of the products also to the gas phase, the MBO will start reducing to MB at a particular point in time during the process. Then we also assume that the tray liquid holdup and reflux drum holdup are constant. And then the vapor boil up rate is constant at V, right? So it moves constantly. It's not being affected by the walls or anything. Then the reflux drum, the column trays, and still pot are all initially filled with material, which we call the composition, XBOJ. So it could be XBO1, 2. If there are two components, it's going to be XBO1 and 2. You get it? Yes. So now, our objective is to write the mass balance for this system. How do we go about this? So the first thing to do is to consider the still pot. So we say that the change in mass in the still pot with time is equal to negative D, which is the distillate. Because the distillate that we are removing, if you look at the reactor, let me come here. It's a badge, right? Let me explain this so that we understand it better. This is a badge reactor, so we don't have input. We don't have input and then output per se. We only have output after the badge is done. But even the output, we are not taking all. We are only taking only the distillate out. So you see that initially there's no input. So ideally, we're supposed to have this to be what? The changes in MB over DT should have been equal to what? The input, right? Input minus output. But there's no input because we'll put everything in and close. We don't inject. There's no flow in. It's only at a certain point in time we'll take out what we call the distillate at this point. You see? So therefore, the equation here, accumulation is equal to input minus output. There's no input term. It's going to be only the output term. And so that's why you see that the total mass balance equation in the pot for the system is equal to this. And this is negative because we are withdrawing part of the product out of the system. Having done that, you now write the component balance equation in the pot. So the component balance equation in the pot is given by what? The fraction of this at a particular point of a certain component. So let's say if we are looking at component 1, it means that it's going to be D. This B is the total mass of everything there times B1 delta T should be equal to what? Input and output. Remember. So what do we have? Something is going in. The gas is going into what? The reflux and then vapor. Yesterday we realized that the vapor phase mole fraction is mostly what? X, right? And reflux is liquid. So sorry, vapor phase mole fraction is mostly Y, and then reflux is liquid, so it will have X. So we are now going to say it's going to be equal to the input is what? Let me go back here and explain this. Input, you see, reflux is coming in again here. So that's the input into the system. That's the reflux. And what is coming out here is the vapor. See, and the reflux is coming in. So that's why here we have the input to be the reflux. Then we look at the percentage of the one, that is one in the reflux minus V times the fraction of one inside the vapor phase. So this one here is the component mass balance for all. So if there are 10 products, you write all this for all the 10 components in the system. Then this is a constitutive equation. You remember that this will help us to find this value. And when you find this value, we can use this is equal to, I think it was equal to xi, right? So when you do this, you can represent it and change the y. And you can have all the terms in terms of x, and then you solve it. So you can do that. All right. So when you finish this, you are done with the still pot. Then you now also have to write the balance equation for the trays. Because on each tray, there's going to be what? Input and then output. There will be liquid here, liquid input, liquid output, gaseous, vapor input, vapor output, liquid input, liquid output. So because of that, we are going to write for that also. And that's what you have here. So for the tray, the mass of any component that comes here will be equal to what? In the reflux, the reflux drops in, right? The input comes from the reflux, remember. So the amount of reflux coming here and the amount leaving on the tray, amount of reflux coming, amount leaving, and then the vapor phase that is going out, that's the output, the vapor that is leaving the tray. So the vapor on the tray, the fraction minus the vapor out of the tray, then you have its own constitutive equation. Then you do the same thing for the top tray up to the last tray on top. So it's going to be similar. Mass of the product on the top tray will be equal to the reflux minus the volume on the top tray plus the vapor times the mole fraction input to the tray and then the mole fraction outputs to the tray. Then you have this one's also constitutive equation stated here. All right. When you're done, you now write the last equations, which is the reflux drum. So you must also write for the reflux drum. And like I said earlier, the reflux will be equal to the V minus the distillate, which is stated already here. And for the component analysis in the reflux, we're going to say that the composition of each component in the reflux, that's this one, is equal to the input. Now you see that this time the input in the reflux is the vapor. Is the vapor that is coming in here. This vapor, this is the vapor line. This is the vapor line. And that is what is coming into the reflux. So this now becomes the input. Then the output is what we take out. And then the distillate. So you see that the output of the reflux is 2. Is the distillate here. And then the amount we put in. So that is why when you come here, you see that we are adding the R and the distillate together. So reflux plus this times the mole fraction in it. Then that becomes the component balance. for this. Any question? So, in conclusion, we have talked about three different reactors here. Normal batch reactor. We established that for a normal batch reactor, the total mass balance in terms of volume, the T, or the total mass balance is equal to 0 because the inputs is equal to the outputs. So there's no accumulation. Then we went further to talk about the um, individual component mass balance for a batch reactor. And then also we went to write the energy balance for a batch reactor. Then we went forward to establish the equation for a semi-batch reactor. And then we also established another one for uh, a batch distillation with pull-down. So all these equations we've established are for batch processes. Batch processes means that you just put in, run, then you take out your smell. In our next class, we will talk about continuous processes and then also processes that involve mass transfer. So with that one, we will have to include the Flick's law of molecular diffusivity in the equation. Yes. So, you have any question so that we can talk about it? If there are no questions, I would like us to talk about the weekends and then we see. So, when should we have our next class? Because there's Easter coming in. If I don't talk about the Easter, some of you will be like, Charlie, this guy, he doesn't want us to have time to celebrate Easter. So I want your ideas on this thing. Because Easter is a big one. People want to
By the
celebrate.
way, hello, Doc.
Yeah, you can talk.
Hello, Doc.
Yes.
Hello.
Yeah, I
Please, can we get this in the video? Yesterday's one today.
I've uploaded everything in the Dropbox. So every time I upload it,
Yeah,
even
yes,
I've
yesterday's one is
uploaded the
uploaded.
slides.
Me, I went there. Okay,
Just go to the
okay.
folder. I've
Oh,
even
is there?
uploaded the latest slides. I keep uploading the latest slide in documents. So don't worry, you'll get
Yeah,
it there.
yeah, it's true. Today I even downloaded yesterday's one because I was almost
Okay,
making
okay,
it.
okay. Thank
Yeah. So
So
after this,
about the weekend, what time do you want us to meet? You give me the proposal, and we will also try to adjust if we have problem.
no, I don't know about you guys, your programs, but for us in university, we have holiday Friday, Monday, but I don't know about you guys. So I can't also
Mm,
have classes
so,
on when the university says we shouldn't have class. I mean, I think it won't be fair. I won't be fair to you
okay,
guys. Yeah.
okay. Ah,
I can't use my own personal
then,
ambitions to push it on you guys.
mm, so that means that we have to meet next week, Monday or Tuesday.
Yeah, if you guys want to have time for your Easter, I mean, it's good. It's for you. If you think you want to spend time with family or
Okay.
something, I
So,
think.
hello, colleagues. What do we say? Can we have some lectures to finish? So, if we can finish it up, it's just 1 hour for 2 hours. If we can finish it up, perhaps tomorrow, Monday.
Oh, if in my opinion, if you can do it on Saturday and Sunday, I mean that's fine.
Yeah, because the Friday and
Okay.
the Monday is very important. Eh?
Yeah, it's very important. I will need to.
Emma, also talk to us.
you. I say that's for me. I'm okay with it. Any proposal, I mean.
Okay.
So the
Yeah, Emma.
Saturday, Sunday. Next Sunday is another major day. So Sunday, I'm not sure. It's
Yeah, you see the Easter program. That's the issue. I mean, I think
mm,
Then
Then what?
Monday will be
What
okay.
about Monday? Yeah, Monday will be fine.
Yeah, Monday
We can do
evening, I
it
Monday will
think.
be
Saturday,
fine.
maybe. We can do it Saturday, either in the morning or afternoon, because we go to church in the evening. So if
Then
it is in the
what about
morning or
Monday?
afternoon,
Monday will be fine. Oh,
Yeah,
Monday evening, I think everyone
yeah,
is free. There's no program. Monday, the programs will be daytime.
yes, yes,
yes.
yes.
yes, yes.
All right, so I think it's okay.
Yeah.
I'm okay with that. Yeah. So we can go
Monday our
Monday,
usual
Tuesday,
time.
Wednesday, then we finish. Yeah.
Okay.
The time frame for Saturday and Monday, please.
Come again, Cornelius?
Yeah, I'm asking the
I
time
said,
frame. Like, which time are
Sat-
we meeting for Saturday and
No, we
Monday?
said
Like,
Monday evening. So Saturday, I think.
in the evening.
Uh,
Oh, okay.
so we'll meet Monday evening.
All right, that's
it's
fine.
my Saturday. Are we meeting, sir?
No.
No, we're not
No,
meeting on
Doc.
Saturday and
Are we
Sunday.
doing
It's
Monday,
Monday.
Tuesday, Wednesday?
Yeah, so we'll do Monday, Tuesday, Wednesday, then we'll wrap up.
Okay,
Okay.
Oh,
okay,
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 okay. All
Hey,
right, no
but
problem.
okay.
hey,
That's okay.
can I chip in
So
there?
maybe
Since
I'll
Monday,
send some. Maybe I'll send some quiz B, so that later we'll see how to do it.
For us to do
okay.
before. Oh, okay, that's fine.
Yeah.
Dr. Babu, I
Okay.
think the next model
Yeah.
starts on 21st. That is also Monday.
Okay, that's true. Though
Which
it
one
will
is it?
eat
Is it
into another.
thermodynamics?
Yes.
I think
But
so.
you are
Yeah.
yet to start
No.
registration, right?
It's advanced petrochemical synthesis.
And that's Dr.
Advanced
Marfo.
petro.
Hey,
Of a
Have you
mouthful.
registered?
Uh-huh.
Have you started
yeah.
registering?
No.
And so don't
But
worry. I will.
when it's time like this, I mean, and dog, then let's squeeze and do it within this week. Because
But the administrator recommended that we should inform her a week earlier. We should not wait till the D-Day. So, police, if we will do it, let's send her a message today and tomorrow so that she'll be aware and inform the lecturer.
Bro,
then dog, let's do
Uh,
something about this week. This thing, I think it will help us.
All right. So
I think
let's see.
Saturday.
Don't
mm,
worry. I can lamp it up for you guys. No problem. I'm fine.
okay. Okay. So we'll meet on Monday.
All right. Monday evening. It's fine.
Yes, sir.
Yes. Monday evening. I think by West, if you guys will start the model, it might be on Wednesday or something. I'll talk to Dr. Mafu so I
Wednesday.
can we
Yeah. At
can do
least
Monday,
yeah,
Tuesday.
start
yeah.
on Wednesday.
Talk to him. Talk to him. That's good. Talk to him
Yeah.
first.
All right.
So I'll talk to Dr.
Uh,
Mafu, then we just I'll give us some 1 or 2 days. Then
okay.
I'll give you guys some small take home exams. I think shouldn't be difficult. Yeah.
Okay.
So we need to take over exams, or we will still do another assignment again.
Do you want to use that assignment for your exams?
But no, I just want to find out. Are we doing
Oh,
assignment
I
at the
can
same
do
time they
that.
take home? Oh, okay. I
I
just
can do
want to
it
know.
too. I can do it one. No problem. I just have to combine, right?
No, like let's do something like one at a time. If not,
Okay. All right.
you can
No
give us an
problem.
assignment. Then later we can do the.
Okay. Yeah. So thank you guys so much. Then have a wonderful Easter celebration. Mm.
All right. Thank you, though.
Okay. Bye.
Thank you, Doc. Thank you.
Sure.